Okay, hi everyone. So today we're doing related rates. And related rates is what people perceive to be a very difficult subject. Okay, people believe it's a very difficult subject. And to wrap your head around it, yeah, it is kind of difficult. Okay, it is kind of difficult. Now, what is related rates? In my easy way of explaining related rates, it's just rates. Okay, and I call it related, or they call it related. I feel like it's because it's related to other things. Like, here's example, a dumb example, but here's example. Okay, if I have a ladder on the side of a building, right? Right. And what happens if the ladder slides down? Okay, so this is a ladder that doesn't bend, it doesn't shrink or doesn't grow. So if the ladder slides down one way, doesn't this base slide out this way? Right. So eventually it'll be like this, and then eventually it'll literally sit on the floor. Right. So the values are related. As I change one value, the other value changes. Another example that they'll oftentimes give, well, not oftentimes they give, though, for instance, let's say I am Mr. Ko, and I'm standing, or I'm sitting apparently in a yoga position, right? Looking at a train, okay? And as a train is coming toward me, toot toot, right? I'll give it like a train is coming toward me, right? What is the distance, or what is the speed at which the train is changing toward me, right? So as this train goes this way, values are going to change, and these rates are going to change. So this rate's going to change, this rate is going to stay constant, this rate is going to be constant. So the law of values are changing, and afterwards, what if the train is over here? Now how is it changing? So these rates are constantly moving. Another example they'll give is, for instance, a balloon that's blowing up. Right, you end up with a little tiny balloon, and then as you blow it up, I can ask you, what is the rate of volume changing, dV over dt? How is that changing? Well, that's also related to the radius, right? As a balloon gets blown up, the radius changes. Maybe I can ask you, how is the radius changing in relationship to the volume changing? But if you notice, a couple things we've been talking about is we keep using the word time also, because when we're using rates, for the most part, it's related to time for a majority of our problems. So we're going to do a couple of quick experiments here, and I'm going to show you guys the basic principles that you will be doing to take the derivative, essentially. So if you looked at the last, pretty much chapter 5, pretty much our most terrible chapter in the world when it comes to application, it's that we've been having to create oftentimes our own equations to solve for the situations. Like we'll have to say, oh, that's a triangle, maybe I'll use Pythagorean theorem. Or, hey, that's area, that means I have to use base times height. You have to come up with these equations yourself. Oftentimes related rates, they might give you the volume equation, sure. But if it's a triangle equation, like this latter one, they're going to expect you to come up with this Pythagorean theorem yourself. Okay, so I'm going to give you guys the one of the hardest parts about this is just taking the derivative. So just starting off with some tools. If I give you x plus y plus is equal to x squared plus y squared is equal to c squared, right? I want us to, let's say this is my starting value. Take the derivative with respect to t. Now what I'm saying, instead of taking like derivative d over dx, oftentimes before we would say, hey, if this is y, we would take the derivative d over dx. We're not going to take the d over dx, we're going to do d over dt. So d over dt, that's what we're going to do to this problem. And you tell me if this is something new or something we've done before. Because I would say it's something that we've done before, except I just changed the letter. So here we go. We're going to take the derivative with respect to t on both sides here. So x squared plus y squared equals to c squared. Right? So if I do something one side, I'm going to do it to both sides. Obvious, yeah? Now, you might say, Mr. Ko, what the hell is going on? But I want to remind you, when I take a derivative of addition, here, is it that hard? No, remember the derivative of them separately. So the derivative of x squared, please careful, chain rule, the derivative of 2 is 2x, and then what's the derivative of x in relationship to dt? Is dx over dt. Okay, tell me if you need me to write this bigger. Or to rephrase this. Let's try this again. The derivative of y squared is first exponents first. 2, leave the inside alone. What's the derivative of y with respect to t? dy over dt. Keep going. What's the derivative of c squared? Exponents first, because power rule. 2, leave the inside alone. And then the derivative of inside is dc over dt. That is it.
Why do we repeat the dy over dt at the end of each one?
Okay, so let's talk about chain rule. Let's go back to something that we do know. What is the derivative of x squared? That's just 2x, right? We just say 2x, right? But
Yeah.
remember, it's actually chain rule. It's actually d over dx of x squared is really first do the exponent 2, leave the inside alone, and then we multiply by the derivative of the inside, chain rule, which gives us our invisible 1. Okay, so if it's d over dx, great, they cancel out. But what if I don't write x, but I write t instead? Do they still cancel out? They don't. And that's what we wrote here. We wrote t here.
We're not so if we write d over dx, it's going to be a mistake.
D over dx. Yes, because if I say time, let's say if I'm talking about speed, right? Velocity, miles per hour. You don't say miles per x. And when we're talking about rates, a rate is referring to time for the most part for us. Okay? So we're going to do the same process to a different equation here. Here's my volume of a sphere, 4 over 3 pi r cubed. And we're going to take the derivative of this. Okay? So we take the derivative of this, d over dt of v, and d over dt of 4 over 3 pi r cubed. My first goal is to show you the derivatives are not hard. Okay, they're not hard. We just have to practice. When we've done these before, just remember your rules. Okay, so can I take the derivative of v? No, it's just dv over dt. Are you okay with that? Okay, just take the derivative of v. Can't do it. They don't cancel out. Just write it. And that's what we did back here. The derivative of x with respect to t. Can't do it. Leave it. Derivative of y with respect to t. Can't do it. Leave it. Okay. And then let's do it on the right side. The derivative of all this. Oh my gosh, that looks so difficult. But remember, what is 4 over 3 and pi? Are they variables?
They're constants.
Constants. So just write them down. Easy. 4 pi over 3. You just hang out there while we do the real work. And then the derivative of r cubed is 3 r squared dr over dt. Okay, let me do that really quick, so in case you guys don't see it.
Mr. Ko,
Yep.
if since pi is a constant, wouldn't it equal 0?
No, we're multiplying. It's not an addition problem. So unless you want to do product rule, we can do that. But remember, this is constant multiple. What is the derivative of 4x squared? It's 4 times 2x. Remember, the 4 just hangs out. It says, hey, I'm going to wait outside while you do your dirty work.
Okay, that makes sense.
If you want to do product rule, we could do product rule, and sure, just to believe, so you guys believe, the derivative of, let's use this, for dt of 4 over 3 pi, leave the back alone, plus the derivative of the back, 4 over 3 pi, d over dt of r cubed. What happens to the derivative of this? That's a 0. 0 plus what we got before.
Oh, so it'll just cancel out
It
no
was going to
matter
cancel
what.
anyways,
Wait.
right? So if you do
Okay.
use the rule, it's going to cancel out. That's why you never do it. Okay. So it's just
Mr.
this.
Ko,
Yes, sir.
but if we get dr over dx instead of dr over dt, it's still not gonna cancel out.
It's not going to, and it's not supposed to. It's not supposed to, right? We
Okay.
always choose what we're going to take the derivative based on. Like example, why do we call the derivative slope? Well, it's because isn't dy over dx really rise over run? So we
Yeah.
chose dx because we want to base that on an x value, our run, rise over run.
Mhm.
We never say dy over dy because what's the point of that? Okay, so we're choosing to use dt because we want to make this based on time. Okay, so
Yeah, I see.
that's our derivative. Now, what does this mean? Okay, what does this mean? A dv over dt says change in volume over change in time, right? Which is the rate of volume versus time. This means how much volume is changing over time. To use this in plain English, if I say miles per hour, isn't that how many miles, like distance that you traveled, the distance that you traveled over a time? That's what miles per hour means. If I drive 100 miles in 1 hour, not Mr. Code doesn't do that, but if I do, I'm driving 100 miles per hour. That's how much I'm changing based on time. So what we're doing here is if I ask you, what is a change in volume over time? That's dv dt. What do you think dr dt stands for?
Change in radius over change in time.
That's it. It's the speed at which your radius is changing. So the cool thing about this is, let's go ahead and give you a small illustration of what really is going on here. If I give you a sphere, oh, come on. Here's a sphere. The only value we have in a sphere is not just the radius, right? And then a sphere kind of looks like a 3D sphere, right? Okay, a sphere. And if I say how fast, imagine if I'm blowing air into I have a little pump here, right? And I'm pumping air, boom, 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 right? Woof, 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 woof. Okay? I can tell you how fast the volume is changing with relationship to how fast the radius is increasing. And that's what this equation says. Hey, you tell me the radius that we're at, how fast the radius is, how much air you're pumping in to increase the radius. And then, or other way around, I can tell you how much volume is being pumped in. And then I can tell you how fast that radius is growing or shrinking. Okay. So let's do one more derivative, and we'll see this one can get harder, right? And the other one is, let's say the derivative, dv dt of the volume of a cone. So here's the volume of a cone, volume. And then the volume of a cone is 1/3 pi r squared, pi r squared, I'm sorry, squared h. Okay, or some people write this as pi over 3 r squared h. Okay, if you don't know where you come up with the volume of a cone, it's really just a cylinder. This is pi r squared, right? And this is my height. And then we divide it by 3. Oh, darn it. Sorry. A cone is always 1/3 of a cylinder. And my terrible joke is that whenever you sharpen your pencil, right? When you sharpen your pencil, don't you want a sharp peak? So don't you cut off, or don't you try to make it into a cone? And you're really throwing away 2/3 of your pencil. If you spend $1 on a pencil, you've only really used 33 cents of it. Good job. So if I ask you to take the derivative of this guy, now here is a problem with this guy. If you guys take a look here, I want to ask you guys, what special rules will I need to take the derivative of this problem? Let's write pi over 3 r squared h. Okay. First, on the left side, is it hard for me to take the derivative of v? No, right? It's just dv dt. Is it hard for me to take the derivative of pi over 3? Nope, that's just a constant. So I'm going to write pi over 3 on the outside. But is it hard for me to take a derivative of r squared and h through multiplication? See, they're multiplying, aren't they? So then we have to use which special rule?
Product?
We have to do product rule. We have to do product rule, right? And that's the problem when you have more than one variable. Do you really want to do product rule? Seems like a lot of work to me, right? But let's do it just because we can try. The setup for product rule is derivative of the front, leave the back alone, plus the derivative of the back, leave the front alone. Okay. And just to do this derivative, I'm going to pi over 3 in the front. The derivative of r squared is 2r dr over dt. Please tell me if you need help with that. If you need help with that, please let me know. The derivative of h, hey, dh over dt. That's just what it is. It is not 1. It is not 1. And then r squared. Does anyone need help with that? So
Wait, Mr. Coles.
Yes.
So can you explain why we put like 2r, but then we put dr over dt?
Okay, so I'm going to do it on the right side, okay? If I take the derivative of, okay, I'm going to do a problem that we did before, like old school, of x squared, okay? You would take the 2, put in the front, don't we? That's power rule. And then don't we just leave it as x? And the reason why is because this is actually chain rule. Take a derivative of the outside first and leave the inside alone. Followed up with the derivative of the inside, which is just 1.
All right.
Okay. But if I switch this variable to y, d over dx of y squared, we still take the derivative of squared first. So it's 2, leave the inside alone, and then dy over dx. But this one doesn't get canceled out. And that's what we did when we did something called implicit differentiation. And that's kind of what we're doing here. We're doing the implicit differentiation. Except we're switching this to like a different letter, okay? Okay. And so we're just saying that's how we take derivatives, okay? That's how we take derivative, folks. Now, do you really like us doing product rule for this? No, no one likes doing product rule for this. So we will see some problems where we can escape product rule by swapping out the variable. So there's only one variable. Okay, we're going to swap it out. Now, I'm going to talk about some questions that you guys might have in homework. And some homework questions will be something kind of dumb. They'll say, for instance, v is equal to 4x cubed y squared. Okay, and then they'll ask you, what is the derivative of v? What is dv dt? Okay, what does dv dt become? Well, how do I get from v to dv dt? I take the derivative. And this is what they'll mess with you. Some question will say instead, hey, tell me dx dt using this equation. Or tell me dy dt. Oops, that should be a t. dy dt. Tell me, solve for this. Well, how can I get this into dx or dt? Or dy dt? Just take the derivative. That's it. That's a gimmick. You want the derivative? I'll give you the derivative. Sure. To solve for dv dt, we need to take the derivative of 4x cubed y squared. That's going to need product rule. So take out the 4 first. Derivative of x.
Mr. Sorry to interrupt. I think you have an echo.
Oh, I do. Sorry. I think it's because of my volume on my tablet. A little bit better now? and then leave y alone. I guess go with this. So that's a big parentheses, right? Derivative of the front, leave the back alone, plus the derivative of the back, leave the front alone. That's the basic principle. Do not overthink it if you don't have to. Now, what if I give you some caveats here? What if I say x is a constant? Would this problem become easier? Let's say this again. If x is a constant, v equals to 4x cubed y squared. If x was a constant, hey buddy, you're a constant now. Would this problem get any easier?
Yes.
Yeah. The derivative of v is still dv, but isn't 4x cubed all constant now?
Yes.
You guys are just constant. We only have to take the derivative of y squared.
So whenever it's a constant, we just don't take the derivative. Alright.
If you can see my head shaking, that's right. Or if we do take the derivative of it, it would be 0. What if I told you y is the constant? Okay, for v equals to 4x cubed y squared. If I can tell you y is the constant now, fine. Hey buddy, you're my constant. 4y squared gets kicked out, and we only have to take the derivative of x cubed. So one cool thing is that though these related rates problems may be difficult, read them because sometimes they'll give you a hint that one side is going to be a constant. One side will be a constant, which makes the problem easier. So I'm going to give you guys a example of a problem that we're going to do that. So let's go back to our ladder problem. Okay, I have a ladder sitting on the side of a wall. Okay, give you a couple of ideas. The wall is, let's say, currently at 10 feet tall, just to say that. Actually, no, let's use some easier numbers. I'm not use 10. I'm going to use 8 feet tall. And the ladder is currently 6 feet away. Okay. And using Pythagorean theorem, how long do you think the ladder is going to be? 6 squared plus 8 squared equals to c squared. 36 plus 64 is 100. So our c value is 10. Okay. First to start. My question ends up oftentimes saying, how fast, what is dx over dt? Okay, what is dx over dt? So what here would be constant? I want you guys to think about it. If this ladder is sliding down and sliding out, okay, sliding down, sliding out, is the y value or the x value going to be constant? No, right? Because they're moving, they're in motion. But the ladder itself, for all these problems, is always locked into place. That's a 10-foot ladder, and it will stay a 10-foot ladder. So if we set this equation, x squared plus y squared is equal to c squared. Okay. I'm going to give you also one hint. Dy over dt is falling at a rate of, let's say, 2 feet, negative 2 feet per second, okay? Per second. I want you to take a look at a couple of things I've written here. First, I've given you a couple of values for the x's and y's. I've also given you a dy dt, and I'm looking for a dx over dt. So how can I go from a triangle equation to a dx dt and dy dt? What do you think the answer is? Just take the derivative. And that's really how we relate these. We say if you have a dy dt or dx dt, that's the derivative. I can get from my base equation to that equation by taking the derivative. But we're going to do some little cheats here. First, you cannot plug in any number that's not a constant. If I plug in 8, it's 8 1 second, it's 7 the next. Can't use that one. 6, it's 6 1 second, it's 7 the next. But which of these values here is a constant?
The size of the ladder?
Size of the ladder, that's right. Take a look here. That is just 10 squared. So we made the problem easier by plugging in constants. You can only plug in constants because they're not going to change. And that's what we kind of demonstrated back here. That if I plug in a constant, the problem becomes easier, but we can only plug in constant values because they're not going to change. So that's the problem. Now, let's go ahead and try to get to dx dt or dy dt. We just take the derivative. The derivative of x squared plus y squared is 2x dx over dt plus 2y dy over dt equals to 0, because the derivative of a constant is 0. Now, I want to show you a side note. Okay, what if I forget to plug in the constant? What if I left this as c squared? Then this would have been 2c dc over dt, okay? What if I did that? From this step on, we're going to plug in every value we know. We know that x is what? Looking at my little picture there, x is 6. We know that. We know y is 8. At that very instance, y is 8. We know dy dt. They told us dy dt. That was going to be negative 2. The only thing we don't know is what we're solving for, dx dt. So this becomes an algebra 1 problem now. The right side is 0. So if I rewrite this, this is going to be 2 times 6 dx over dt equals to plus 2 times 8 times negative 2 equal to 0. Now, here's a side note real quick. Remember how we said, what if I forgot to plug in the constant to make the problem easier? What is the change in the ladder? Is the ladder changing at all? As it's sliding down, is the ladder changing at all? It's not, right? So isn't dc over dt equal to 0? Hey, it was going to be 0 anyways. Oh, Mr. Koba, it's 10. What's 10 times 0 though? 0. It was going to be 0 anyways. So even if you forget, remember the derivative of a constant is 0. It's not moving at all. And then we can go ahead and solve the rest. 12 dx over dt plus, this is, oh, that's a minus now, right? Minus 32 is equal to 0. Dx over dt is equal to 32 over 12. And we're going to say this is feet per second, because that's the units we were using. So if the ladder is sliding at 2 feet per second, which is pretty darn fast, okay? Imagine if something dropped 2 feet per second, you are falling, okay? The ladder would be sliding out at 32 over 12, which is a little less than 3 feet per second. So it's going to hurt when you hit the ground. Okay, it's going to hurt. But the idea is that we can calculate these related rates. As one rate changes, so does the others. Everything in it is involved. Like your elbow is connected to your hand, and if your hand moves, your elbow moves. Or the other way, your elbow moves, your hand moves. They're all related. Okay, so here's another example of the volume equation that we talked about. I can ask you, how fast is the radius changing? So here's the volume problem of a sphere, okay? Okay, so I am pumping up a balloon. Okay, let's say we have a balloon, and we're starting with a radius of 3 let's say 3 inches, okay? Let's say 3 inches. Okay, that's my radius, 3 inches. And then we're going to add air to it, right? We have a pump. Pump, 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 boom, 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 right? And of course, this balloon is going to get bigger, right? Okay. So our volume for this balloon is V is equal to 4 over 3 pi r cubed. I want to figure out how fast this balloon is increasing given the much amount of volume of air I'm going to push into it. Okay, so find dr over dt when dv over dt is equal to, let's say, 3 feet per minute, something like that. 3 feet per minute. Oh, 3 minute cubed. Volume is a cube unit. Okay, so this is a lot of air, I guess. So how fast would my radius be blowing up? Okay, so a couple of things you want to see in a problem like this. First, don't they give us dr dt? How the hell am I supposed to get r to dr dt? They gave me dv dt. How am I supposed to change v to dv dt? Take the derivative. Okay, so we're just going to take the derivative there. In this case, nothing's constant. As I pump in air, the the radius is going to start increasing, so that's not constant. And lucky for us, we only have 2 variables. Yeah, 2 variable problems are the best problems. So we take the derivative. dv over dt is equal to all constant. That's all constant, right? So 4 over 3 pi, and the derivative of, let me write that over, of r cubed is 4 over 3 pi 3r squared dr over dt. All right, so let's take a look if we have everything we need to solve this problem now. First, they told us the radius is 3. We know that variable. They told us dv dt, how much air I'm pumping in at once, is 3 feet cubed per minute. And we don't know dr dt. So we have everything we need to solve for this problem. So 3 is equal to, I'm going to cancel out these 3. So it will be 4 times 9, because 3 squared is 9, dr over dt. So dr over dt is equal to 3 over 36. Oh, is it 36? Yeah, 36. Does that seem like a lot? Well, sorry,
Is it
Dan.
36?
Yes, I forgot the pi. Thank you.
Yep.
So does it seem like the radius is changing that much? It's not. Because remember, this is not per second, this is per minute. So it's 3 cubic feet of air isn't that much. I mean, compared to the 3 inches, that's not a big deal, but over a minute, it's not increasing that much. Okay, but this is the rate at which and this is probably going to be something like inches per minute.
We can simplify that, right?
Yeah. 1 over 12 pi inches per minute. But if you notice, the real calculus here is just taking the derivative. Everything else is critical thinking. Which equation should I use? What am I solving for? What values do we know? What values don't we know?
Doesn't matter that it's in feet.
Oh, did I use inches? Oh, sorry. Yeah, so it should stay as feet. I messed up. Feet.
Alright.
But then also, like, the thing is about, actually, there's a issue. I did make a mistake here. See how this is 3 inches and that's 3 feet? You have to change them so they're the same. Right, so you have to change them so they're the same. So I would probably change, darn it, I should have kept them the same. Let's change this to feet. Here we go, change that to feet. I fixed the problem, change it to feet. Change this to feet. If I could retcon this, I would change that to feet. Okay, 3 feet. There you go. Retcon. The pass. does not exist. So I should keep them as the same. I was just not doing it. Okay, let's do another problem. Okay. Let's say I'm on top of a building. I am dropping a ball down a 30-foot building, okay? I am, this is me, an observer. Okay, this is probably my wife, as it looks like I'm dropping a child now, which for some reason I'm thinking about this in a terrible way. No, this is the ball. I'm saying, hey wife, watch this, I'm dropping a ball off a building, okay? Okay, and then let's say she is, I don't know, 40 feet away. Did anybody wonder why I choose these numbers? Okay.
So it would be easy to Pythagorean theorem.
Yeah. Right. Okay. If I'm going to throw something, a wrench in here. I'm going to throw this theta. Okay. Now, how fast does... Okay. So I'm going to give you guys a measurement. Real quick. What is the rate at which gravity in feet? It's meters per squared, right? Rate of gravity... Rate of falling objects in feet. 32 feet per second. All right, so the chain, if I drop a ball, dy over dt is negative 32 feet per second. Are you guys cool with that? 32 feet per second? That's how fast something drops. If I drop something, that's the velocity. Oh wait, shoot, it's per second. Okay, we'll just stick with this number. Darn it. Okay, so at 0. Alright, let's just take this. In 1 second, it will fall 32 feet. Got it. So, my thing here is, what is d theta over dt? What is the change in the angle once I let go? Once I let go, how fast is this going to turn? Okay. Now, just to say, if I really drop this, it's going to change. But I'm going to say I'm holding onto a string that will drop it at a constant rate of 32 feet per second. Right? To make this easier. In real life, this will actually speed up and this will crash into the ground and break. But there's a string holding onto it that will only release this at 32 feet per second. Again, I'm retconning everything. So can you guys come up with a trig equation that relates these parts that we have described already? Would you use sine, cosine, or tangent to relate theta and dy dt? And maybe this guy too. And
Tangent.
I'm hearing tangent, right? So that's set up with tangent. If I say tangent of theta is equal to opposite over adjacent. You guys go with this? Opposite over adjacent. Okay, which we can describe as tangent of theta is equal to opposite, which is our y value, over our x value. Now, before we proceed to say find d theta, find the derivative, I want to ask you first, are any of these values that we've written here, 30, 40, are any of these values constant?
30 feet?
30 feet? Let me ask you, once I drop that ball, is that going to stay constant?
Oh, no.
No. If this was a ball, do you think my wife is going to run 40 feet to try to catch the ball?
No.
Nope. If this was a baby, yes. But if it's a ball, nope. So the constant part here is her distance away. So we can actually rewrite this. Is tangent of theta is equal to y over 40. You guys cool how I made this problem a little bit easier with less variables? So if we have variables, we can plug those in. All right. Now let's go ahead and try it, and we're going to see that we're still missing something, okay? Let's go ahead and take the derivative. Hopefully you remember what the derivative is of tangent. And here we go. The derivative dv over dt, or sorry, d tangent of theta, and d over dt of y over 40, okay? Here we go. The derivative of tangent is secant squared. Now careful, does d theta and dt cancel out? They don't. That's why we have to write d theta over dt, because that's chain rule. Derivative of the outside, then derivative of the inside. On the right, it's 1 over 40, and then dy over dt. All right, so let's see, what do we have? Do we have dy over dt? That was given. Do we have d theta over dt? Nope, that's what we're looking for. Now, if you please notice that I'm missing a value. I'm missing theta. So what you have to do is we have to actually go back and solve this equation. What is tangent of theta at the very instant of 30 over 40? What would theta have been? So sometimes you have to go back to look for these variables, because it's still asking me for theta. So let's go ahead and tan inverse of 30 over 40. That'll give us a calculator answer of, what is, we're going to answer this in radians. So in calculus, we always do everything in radians. Making sure I'm in radians. 30 divided by 40 equals, and then we're going to shift tangent that. And my theta is 0.643, okay? So we're going to take the secant. Oh, know what? We could have done that. Or here's something kind of cool. If I could write this, 0.643. Okay, that's one thing we could do. But there is a trick here. Here's a trick. Aren't we going to just take the secant of this angle anyways? Look at this triangle, please. What is the secant of that triangle? 30, 40, this is going to be 50, okay? What is the secant of this triangle here? Everyone, please tell me, what's the secant of this triangle? Secant is hypotenuse over adjacent. So what's the secant of this triangle?
5 over 4.
5 over 4. Everyone cool with that? Now, if I took my calculator here, remember how I got 0.64 something? If I hit secant of that, which I can't do, 1 divided, let me see if I can copy that, 0.6435. Oh, I know I can do. 1 divided by cosine, shift answer, last answer is, hey, where'd it go? Point 643 cosine equals, we end up with a 1.2459, which is 1.25, which is our answer here. Here's the thing. You could just use this answer. That's going to be, instead of using this guy, we're going to use 5 over 4 squared. Um, 1 over 40. And then dy dt we said was negative 32 feet per second. Okay. So we can solve for theta, get rid of everything. So d theta
Wait,
over t.
oh,
Yep, go ahead.
where do you get the 5 over 4?
Okay, so I went and solved for theta to be 0.643, okay?
Mhm.
And if I plug in 0.643, we're going to end up with a secant of 0.643 to be something like 5 over 4.
Alright.
Or, don't use your calculator. Just look up the secant of theta from the triangle. So the secant of theta was going to be hypotenuse over adjacent, which is going to be 5 over 4. The point is that I didn't even need my calculator, and that's actually a trick. You might see a problem like this, and you might think, hey, I need to look for theta. But really, theta is already given in the triangle. Okay, and then this is going to become some messy. I'm just going to write it. Negative 32 over 40 times 16 over 25. And I'm going to leave like this, okay? So we're done. And that's going to be our radians per second. So this is how fast the angle is changing when I drop my ball from the roof. Okay, so let's go through the related rates part to just reiterate. So first step is to come up with an equation that illustrates what's going on, making sure that you're taking advantage of everything that you know already. They want to look for d theta dt. That means I need a theta equation. Pythagorean theorem will not work here. If they want theta, that's not Pythagorean theorem. Pythagorean theorem is x squared plus y squared equals to c squared. There's no theta here. So I chose tangent because I knew these values here. Okay, once we had our tangent equation, we took the derivative of our tangent, and we realized, hey, d theta, that's what we wanted, and dy, that's what we have. I need to look for theta. Darn it, I missed a variable. So you can either go back and solve it or realize secant theta is in the problem. Secant theta was 5/4. Okay.
Can you scroll down a little bit, please?
Sorry. Okay, so I'm gonna give you guys, let's do one last question, and this is a question from your homework, and this is question number 9. It looks kind of crazy, okay? No joke. Let me go ahead and log in. I need to go through a long way. Let me pause here. Okay, so let's take this question as example. Sorry, the font's a little small, but sand is falling from a conveyor belt at a rate of 10 meters cubed per minute. So when you see something that's cubed, is at a distance, a area, or a volume. So when it's cubed, it's going to be a volume, okay? Onto a conical pile. So you can think of a conveyor belt, and then dropping sand into a pile, okay? And then there's like a box here, okay? Box of sand. All right, cool. You guys get the idea? Hopefully. The height of the pile is always 3/8 of the base of the diameter. Oh my gosh. The height, oh gosh. The height is always 3/8 the base of the diameter. So here's the diameter. We'll call that letter D. And the height is always 3/8 of the diameter. Okay, hopefully I didn't read that wrong. The height of the pile is always 3/8 of the base of the diameter. How fast are the height? Okay, so how fast? When I say how fast, that's a rate. So how fast is the height changing? This is my height. How fast and the radius of the pile, and then the radius is dr over dt of the pile changing. When the height is 8 meters high. 8 meters. Okay, give your answer in centimeters cubed. Okay, so first question is, what is the rate of the height changing? Okay. Now, my question to you is, first, do we have an equation to describe what's going on here? Okay. Do we have a way to describe? So they gave us that the dv over dt, that's how fast the volume is changing, is 10 meters cubed per minute. You guys okay with that? Okay. So can you think of an equation that has volume, has height, and has radius to describe this picture on my left?
Volume. No.
Volume, perfect. The volume of a cone is equal to 1/3 pi r squared h. Okay? So, one thing for sure we're looking for dh dt, right? We're looking for dr dt, and we have volume here. Now, my first question to you is, do you really want to take a derivative with R and H? Well, you probably don't have experience, and the answer is no. You want to take a derivative with all these variables if possible. So there's actually always a trick to these cone problems. There's always a trick to these cone problems. And the trick is to replace either an R or H with the other guy. Can I represent R in forms of H, or can I represent H in the form of R? So we actually have that ratio right here. Take a look over here. I'm going to draw this a little differently. Okay, so I'm going to call this R and call this H, okay? So in any cone, right, in any cone, there's always this ratio that exists. The ratio exists is that the R and the H always will equal to each other. Okay? These are from geometry, okay? So here's the idea. If I told you the height is 8 meters, okay, then if I plug in 8 meters here, okay, the height is 8. If the height is 8, okay, the height is 8, what would everything else be? So this is 3 over 8d is equal to 8. That's our height, right? Remember, that's our height. So what would the diameter be? At this instance, this very instance, what would all the variables be? Multiplying this around, d would equal to 8 times 8 over 3. The diameter is 64 over 3. But do we want the diameter? Nope, we've been working with radius. That changes the radius. That means the radius is 32 over 3. So here is the trick to dealing with us changing one variable for the other and for cones. So this works for almost all cones. If I told you the radius is 32 over 3, the height is 8. So what we do is we say h over r is equal to 8 over 32 over 3. Take a look at this ratio here. H over r is equal to the ratio 32 over 3. We can rewrite this ratio. 8 over 32 is 3 over 32 multiplied by the reciprocal, which is 3 over 4. So h over r is equal to 3 over 4. Here is our magic ratio. Why did I call this a magic ratio? Is because if I don't want to take a derivative with r and h for all cone problems, what we do is we substitute h is equal to 3 over 4r. Or if you want, you can say r is equal to, if I flip it, r over h is equal to 4 over 3. R is equal to 4 over 3h. Whichever one you want to use, that is 100% up to you. I am going to solve for h first. See how I'm going to solve for h first? So I want to get rid of all my r's and write them in terms of h. I'm running out of space. I'm going to jump over here to give myself more space. So I'm going to rewrite this equation now. V is equal to 1 over 3 pi. R is going to become h. So we're going to say r is going to become 4 over 3h times h. Please take a look at what I did here. Instead of doing volume equals to radius and height, I just said volume is now just a height equation. And this is actually the super gimmick. If you want to take the product rule, do it. I don't. I'd rather just substitute it, spend a little time with fractions, and we're going to end up with 16 over 9. Rewrite that as volume is equal to 16 over 27 pi h cubed. I'm going to tell you this derivative is going to be 1,000 times easier than me doing product rule. 4 squared is 16. 3 squared is 9. That's how I got 16 over 9 times 1/3. That gives me the 27 on the bottom. h squared times h is h cubed. Now, folks, I want you guys to take the derivative of this problem now. How hard would it be for you to take the derivative of this problem now? The derivative of v is dv over dt. These are all constants, right? So it's just 16 over 27 pi. The derivative of h cubed is 3h squared dh over dt. As a reminder, we are solving for dh over dt. But don't we already have h? Don't we already have dv dt? We have everything else in this problem to solve for. These problems can be very daunting. Yes, there's a lot of steps to it. But when it comes down to it, it's really just actually a lot of algebra 2 and some clever thinking. So if I rewrite it, it's going to be 10 is equal to 16 over 27 pi. I'm going to plug in 8, which is 64. 64 times 3 is a huge number. 3 times 64. I'm going to go ahead and cancel out these 3's here. It becomes a 9. And then we have 10 is equal to 64 times that. 16 times 64. I think I did that right. The height is 1024 over 9. I'm going to pi dh over dt. I'm going to kick this all over. It's going to be 90 over 1024 pi on the bottom is equal to dh over dt. Okay, I'm going to jump over here to see what the answer is. See if it's something close to what we got. 2.518. Oh, they switched it to centimeters too. Why is it in centimeters? I wonder. 2.518.
It's an evil program,
90.
not made for learning.
I know.
Because
Yeah,
it
it's
will have
just
a
my
lot of
lab being
decimals.
awful. Classic
I got
my lab.
2.799. That's the value I got. And this is, looks like this should be in meters. So how do we get this into centimeters? We multiply this by
10.
100, right?
Oh, it was 10.
So yeah. So this was, sorry.
Oops.
I messed up. I translated it in my head already like an idiot. 0.0. Okay. And if we translate that, that will become in centimeters. It's 2.79 centimeters. 2.518. I'm a little off. I wonder why. Let me do this again. 90 divided by 110, 24. The numbers change. Oh, the numbers freaking changed on us. Whenever you hit complete the problem, the numbers changed on you. So yeah, okay. This would have been good. Okay, so this would have been good. Yes, this would have been good. Because we had a 10 here, right? We had a 10 here, but then whenever I hit show me the problem, it changes the number. That became a 9. Okay.
You do number 10 next.
I think we are out of time.
Dang.
So you guys have to go to your next class now. I'll do it offline and I'll record it and I'll put it along with the lesson, okay?
Okay.
All right. So thank you very much, guys. You guys can check out. Okay, like I said, I'm going to do question number 10. So water is flowing at a rate of 70 meters cubed per second, so per minute. So automatically I know the cube part means it's going to be a volume, right? So let me just label that. dV over dt is equal to 70 meters cubed per minute. And then from a shallow concrete conical reservoir, so that means the vertex is down. So a shallow concrete, so I guess we're looking at something like that. This way perhaps? Huh? Right? The vertex they say is down. With a radius base up here, the radius base, is 40. And the height is 4 meters deep. So this is standard, meaning like this is the shape of it. Whether it's filled or not, maybe our water level is going to be down here, right? So how fast is the water level falling when the water is 3 feet deep? Never mind. It's flowing, the water is flowing at a rate of blank from a shallow, okay. So I guess water is leaking out at the volume right here stated. Okay, how fast in centimeters per minute is the water level falling? So we're looking for dH over dt because that's the height of the water falling, right? dH over dt, that's our height. When the water is 3 feet deep, so the height is 3 meters at that time of it falling. Okay, what else do I know? We said the radius here was the initial radius is 40 and the height is 4 meters. Okay, so I'm going to draw this out on the side real quick. This is the triangle we're going to use to relate. My R and my H. My original triangle is 40 in radius and original height is 4. So R over H is equal to 40 over 4. Okay, and we can spin that around. If you want, we can change it H over R. Or we can solve them. H is equal to, so let's do R. R is equal to 40 divided by 4 is 10. So it's just 10H. Or we can solve for H. If we flip it around, H over R is equal to 4 over 40. So H is equal to R over 10. So we're going to decide which one we're going to use here in just a little bit. And since it's a conical shape, we have the volume equation is 1 over 3 pi r squared h. Now, how did I know to use this volume shape? They told us first conical, so it's a cone. And then they talked about volume, right? So I know I'm going to use my volume equation. They gave us a dH dt, so I'm going to use the height over here. So let's go ahead and find the height. So we want to solve for dH dt. So let's change r's to h's. So to change r's to h's, v is equal to 1 over 3 pi. R is, we said, is going to be 10h. So we'll call that squared times h. Rewriting this, the volume is 10 squared is 100. 100 over 3 pi h cubed. Now this problem is so much easier to take the derivative of than having two variables, and that's the goal. Change it to one variable. Pick the variable that you want to solve for. So the volume dV over dt is equal to bring down the 3. That gets rid of this 3. So it's a 100 pi h squared dH over dt. Why? Because the derivative of h cubed is 3h squared and then dH over dt. And we said this 3 divides out with that bottom 3. Like this one down here. Okay, so we have our height, we said was going to be specifically at 3 feet. So that's going to be a 3 value here. Our dV dt, we said was going to be 70. And careful, that's meters cubed per minute. So we're going to change that to centimeters, but I'm going to change it at the end because all my other values have been in meters so far. So 70 is equal, let me a little higher than that. So going up here, 70 is equal to 3 squared is 9. So that's going to be 900 pi dH over dt. Moving these values over, 70 divided by 900 pi is equal to dH over dt. I'm going to plug this into my calculator, see if we get the same answer they do. 70 divided by I'm getting 0.02475, and this was in meters, right? All our values have been in meters so far. dH over dt. And so dH over dt in centimeters, as we multiply that by 100, so 2.4 rounding up to 2.48, which is their answer. Now, their question also is followed up by the second part, how fast is the radius changing? Well, we could rewrite this whole equation here for r, but there's actually a trick. Looking here, if I have h and r, let's take the derivative of h and r and see what happens. Let's actually use this one, it's easier. So the derivative of r is equal to 10h, and sorry I didn't get to this in class, but if I take the derivative, it's going to be dr over dt is equal to 10 dh over dt. And if I'm solving for dr dt, I just need to plug in my dh dt. Okay. So my dh dt here is, so dr over dt is equal to 10 times 2.48, which gives us our 24.8, which is what they got without without rounding, where we did. And then why is it negative? Is because as this is water's falling out, the radius is shrinking. Okay, and actually, we should have said also the height is negative if you wanted, because it's actually decreasing. That's why this would have been negative, and then our radius would be negative. Okay. Okay, let's do one more problem. I thought this would be kind of confusing, and this is problem number 13 on the homework also. The particle moves along the parabola x squared. So a parabola x squared is pretty easy for us to imagine. So here's our parabola x squared. But then they say only in the first quadrant, right? In such a way that the x coordinate measured in meters steadily increases by 4 meters per second. So dx over dt is 4 meters per second. Okay, so they gave us a dx value already, and the parabola goes in this direction, right? That's a parabola x squared. Y is equal to x squared, and we have our x value and our y value, of course. And they said so far the change in x was going to be 4 meters per second, and I represented that by delta x, so change in x. Oh, I guess we could write dt, right? That's how fast it's changing. How fast is the angle of inclination of theta of the line joining the particle to the origin? So we're going to draw a line going this way to the origin, and what is the theta changing? Okay, so what is theta changing? How fast is the angle inclination? How fast is d theta over dt changing of a line? This is a line joining the particle to the origin. Okay, when x is equal to 1 at x equals to 1 meter. Okay, so we need to think of an equation that would have a theta and an x component to it. Well, they didn't tell me anything about the hypotenuse, so I'm maybe going to use tangent here. If I say tangent of theta is equal to rise over, in this case, if I draw a triangle here, that'll be our y over x, right? And we want to find out what d theta and dx is. Now, the reason why I call this y is because that's our y value, right? Now, we could take the derivative of this with relationship to y, but here's a trick. I don't want to take a derivative with a bunch of variables here. So what is y equal to? Y is equal to x squared, isn't it? So we're going to say tangent of theta is equal to x squared over x. So tangent of theta is equal to just x. Okay, so where x is, that's going to be my y value. X squared is going to be my y value. So that's the triangle. That's always what the triangle is going to be, right? If this is x, this is x squared. I'm going to follow that pattern. So all we have to do now is just take the derivative with relationship to t. So tangent, the derivative of tangent is secant squared. Let me just write that. D over dt of tangent theta is equal to d over dt of x. So that's theta. Derivative derivative of tangent is secant squared, and the derivative of theta is d theta over dt. So chain rule, and the derivative of x is just dx over dt. Now, a couple of things that we want to make sure we have here. First, d theta over dt, that's what I'm looking for. We are given a dx dt. We said that was going to be 4 meters per second. Now, the problem is we don't know what secant theta is, and you could go back and solve for secant, but like we talked about in class, could I figure out what secant was given this triangle? The triangle, the situation is given as if x is 1, remember x is 1, what's the y value? Well, x squared is 1 also. So what's the hypotenuse? If you remember, this is a 1, 1 triangle. That's going to be square root of 2. How did I do that? Again, I have x is 1. What's the y value when x is 1? 1 squared is 1. That's why I said this is 1. If I want, I can use Pythagorean theorem, or just remember this is a 1, 1 squared of 2 triangle. So looking at this triangle now, what is the secant of this triangle? The secant is hypotenuse over adjacent. In this case, it's hypotenuse, which is square root of 2, over 1, which is just square root of 2. Square root of 2 squared d theta over dt is equal to 4. Let's go ahead and solve it. We square it. That's going to be 2 d theta over dt equals to 4. Divide both sides by 2. D theta dt is equal to 2. Now be careful, if it's 2, this is in radians, right? Radians. So radians per second. And that's our answer that they wanted.